Welcome to the presentation of our paper G-CASCADE, an efficient cascaded graph convolutional decoding for 2D medical image segmentation. Here I am Mostafijur Rahman from University of Texas at Austin. In this work, we focus on 2D medical image segmentation. So what is medical image segmentation? Medical image segmentation is the process of classifying pixels and generating segmentation map of lesions, tumors, or organs. This is especially crucial for early diagnosis, treatment planning, and post-treatment evaluation of various diseases. Left two images show abdomen organ segmentation, while right images show polyp segmentation. Vision transformers have shown great promise in medical image segmentation because they can capture long-range relations among pixels using self-attention. However, they have limited ability to capture the local relationships. To overcome this problem, previous works use convolution layers either in the encoder or decoder modules of transformers. However, due to the locality of convolutions, these methods have difficulties in preserving long-range relations among pixels captured by transformer encoders. To address this issue, we propose a new efficient graph convolution-based cascaded convolutional attention decoder, G-CASCADE. We have made several contributions in this paper. We are the first to introduce a new graph convolutional decoder that enhances the feature maps by preserving long-range attention due to the global receptive field of the graph convolution operation. It also incorporates local attention through the spatial attention mechanism. We introduce an efficient graph convolutional attention block as the building block of our decoder that preserves the long-range attention of the vision transformer and highlights salient features by suppressing irrelevant regions. We also introduce an efficient design of a convolution block that enables computational gains without sacrificing performance. Here is the G-CASCADE architecture. We get help of existing encoder backbones. We extract features from 4 different stages of the hierarchical encoders and then feed that to our decoder. Our decoder uses a graph convolutional attention module to process or refine the features, preserving the long-range information. Then we have 4 graph convolutional attention module in our decoder for 4 stages. Each graph convolutional attention module contains a graph convolutional block and a special attention block to incorporate local information. Then we use an efficient up convolution block to upsample the refined feature maps and aggregate with the skip connection, then progressively upsample and get the final output. We use segmentation head to generate 4 segmentation output from 4 stages. Now, how do we combine these 4 segmentation maps? We use naive approach, like we add all the 4 prediction maps together with weight. Here we set all the weight equal 1. For binary segmentation, we use the sigmoid activation to get the logits. And for multi-class segmentation, we use softmax. And in case of loss aggregation, we follow the strategy proposed by Rahman et al. In mutation. So in this case, we compute the loss for 2⁴ - 1 combinatorial prediction synthesized from 4 heads separately and then add them up for optimization. We have conducted experiments on 9 datasets that belong to 5 tasks. We do abdomen organ segmentation on synapse multi-organ, cardiac organ segmentation on ACDC, polyp segmentation on clinic DB, Cavasir, colon DB, and endosyn. Skin lesion segmentation on ISIC 2018 and retinal vessel segmentation on DERIVE and SAGE DB1. We use DICE, mean intersection over union, 95% Hodge drop distance, accuracy, sensitivity, and specificity as evaluation metrics in different datasets. And as encoder backbone network, we use pyramid vision transformer V2B2 and a small cascaded merit in all our experiments with pre-trained image net weight. Here is the results of synapse multi-organ segmentation. From this table, we can see that our PBT G-CASCADE improves PBT cascade by 2.22%, and it also improved cascaded merit by 0.22% with 80.8% fewer parameters and 82.3% fewer flops. Our G-CASCADE also achieves SOTA DICE scores in 5 out of 8 organs. Here is the qualitative results of synapse multi-organ segmentation. From this figure, we can see that in the white rectangular box, we highlight the region where most of the methods fails, but our method can correctly identify that region. And we can see that our method has pretty much good overlap with the ground truth, but other SOTA method cannot identify or have false positives in both row 1 and 2. Here we show the effect of different components of G-CASCADE, and from this table, the first row, it contains the baseline without the decoder, so it has 80.1% DICE score. When we add this component, cascaded or graph convolutional block or special attention, it improves the DICE score. However, when we use all these 3 components together, we get the best DICE score, 83.3%, with only 0.342 gigaflops and 1.78 million parameters. So that means we get 3.2% gain in DICE score with minimal parameters. This is the computational complexity comparison with Cascade, one of the competitive method. So when we compare with Cascade, we first compare our UCB, so efficient UCB block. So our efficient UCB block is less expensive than original UCB, and it still get like better DICE score than original UCB. Besides, when we compare Cascade and G-CASCADE, we can see that our G-CASCADE beats Cascade decoder by 0.5% DICE score with 80.8% fewer parameters and 82.3% fewer flops. Here we compare different graph convolutions, and from this table we can see that max relative graph convolution is the best performing with second lowest flops and parameters, and that's why we recommend using max relative graph convolutions in our decoder. To conclude, we introduced a new graph convolution-based decoder, G-CASCADE. Our G-CASCADE outperforms state-of-the-art methods on 9 datasets that belong to 5 2D medical image segmentation tasks. It also surpasses a recent state-of-the-art decoder Cascade with 80.8% fewer parameters and 82.3% fewer flops. Our G-CASCADE can be used with other hierarchical vision encoders for improved medical image segmentation, and it also can be used for other downstream medical image segmentation and semantic segmentation tasks. Please, you can scan the QR code for our source code and paper. Thank you, everyone.